Welcome back. So as the last part of our module on training algorithms and advanced training algorithms for optimization of deep learning models, we were talking about distributed learning paradigms. Basically scenarios where the data is distributed among many participants, and still we are interested in learning a model, maybe a model that's shared among all of these, so it's going to be used by all of the participants, or maybe learning multiple personalized models. Okay, so we talked about different scenarios, for instance, centralized learning, parallel learning, federated learning, and decentralized learning. And we kind of argue that decentralized learning is the one that is the most general. Okay, and we basically discussed some basic algorithms, essentially how to integrate SGD or the variants of SGD that we've talked about in the class so far in the decentralized case. So in this lecture, we're going to talk a little bit more about the decentralized SGD algorithm. So we want to see how it's going to perform in terms of the optimization error in the distributed case. And we also want to identify slightly more precisely the impact of the connectivity of the communication graph on the convergence. Okay? And in the next lecture, we're going to talk a little bit about another concern that might arise in the distributed case, and that's the concern of communication efficiency. So we're going to talk about decentralized SGD. Okay, so let's review what our setup is. So we're going to assume that we have k agents with different loss functions. Okay, what's the main goal? The main goal is to minimize the average loss. Okay, so the average loss, which is basically the average of these individual loss functions for each agent. Now, in the context of machine learning and deep learning, specifically, our loss has this form. Okay, so it could be itself an average loss, where the average, by average here, we mean the average over the training data held locally by agent J. Okay. Now, how are we going to solve this problem? Well, the agents are going to iteratively communicate over a graph to find, let's say, the optimal or the suboptimal solution to this problem. Okay, and this is what this is a sort of an implicit constraint that we are imposing. So we want every agent to have the same solution W star. Okay, so when our iterative communication algorithm ends, we want everyone to hold the same model, okay? And essentially, that means that they should reach consensus, okay? They should reach an agreement at the end of the training, okay? All right. So if you're hoping everyone to have the same solution, okay? And given that the loss functions are different, because in general, the data that the agents have are different. So to find the solution, we have to ensure that the agents can communicate. Otherwise, we don't have any hope for solving this average problem. Okay, so minimizing the average loss. So we're going to assume, therefore, that the communication graph is a connected graph. Okay. So therefore, that means that there is at least one path between any two agents. Okay, so they don't have to be directly connected, but it's fine if they are indirectly connected through communication from multiple agents. Okay, so this is so all of these graphs that I'm showing here are examples of a graph that is connected. Okay, so for instance, in a ring, so if this is agent I, this is agent J, they are not directly connected, but there is one pass here, and there is another pass between the two agents, okay? So similarly in the grid graph, exponential graph, as well as the fully connected graph, there is at least one pass among between the agents. And note that in the fully connected graph, as we talked about before, they are directly connected. For instance, agent I, agent J, they are actually directly connected, which means that agent I can send a message to agent J in exactly one shot. Okay. Now, intuitively, higher connectivity means faster convergence, right? Because that means that the messages can reach their destination faster, okay? But our goal is to sort of make this slightly more precise and see its precise impact on the convergence of decentralized algorithms, such as those that integrate SGD or its variants in themselves, okay? Now, what's an example of a graph that is not connected, okay? So, for instance, when I have isolated components, okay? So, this graph among 4 agents, let's say 1, 2, 3, 4, okay? It's an example of a graph that is not connected. 1 and 2 can communicate, but there is no path, let's say, from 1 or to 3 or 1 to 4, okay? So, these are the cases that we're going to exclude. All right. So let's be a little bit more formal. So basically, by communication graph, we are talking about a graph. So a graph should have a set of nodes, set of edges. So a set of nodes is easy. It's n from 1 to capital K. It's basically the set of all agents. Each agent is acting as a node in the graph. And E is the set of all edges. Okay. So what does that mean? So there is an edge between I and J. If so basically ij, this set belongs to this set E if there is an edge from agent A to agent J. That means that agent I can send a message to agent J. Okay. Now, in general, the communication could be asymmetric. It means that if I can send a message to J, J may not be able to send a message back to I. Okay. So if J is in E, Ji may not necessarily be in E, okay? And I would say a lot of the practical applications could be modeled as graphs that are directed, okay? However, for simplicity, we're going to assume undirected graphs. But I should mention that there are results in the literature for the convergence of basically distributed algorithms when the graph is directly is a directed graph. Okay, but for our purpose, it suffices to just stick to undirected graphs. Okay. Now let's define another quantity. So let n sub I to be the set of neighbors of agent I, and we always assume that an agent can communicate with itself because obviously it has access to its own data, it has access to its own laws. So therefore, I is always among its agents. All right. Now, more generally, we're going to assume that these edges that I'm talking about are actually weighted. Okay. So the communication is weighted such that there exists a weight matrix W that basically governs the communication among the agents. So it's essentially to model the cases where potentially I trust one of my neighbors more than the other one. So if I receive a message from, let's say, the first neighbor, I may want to prioritize that over the second agent. Or another case is that, let's say that I know I'm communicating in a noisy environment. So I may want to prioritize my own messages, right? So my own local information compared to what I receive from the other agents, my neighbors. Because I know that whatever information I have access to is not noisy, but what I will receive from others could be potentially contaminated by communication noise. Okay, so therefore, in those cases, it may make sense to think of the edges as weighted edges. Okay, such that Wij, which we assume is non-negative, is basically the weight of edge ij. Okay. All right. So so let's see what are the implications of the assumptions we've made, for instance, in terms of the undirectedness of the graph on this weight matrix. Okay. So first of all, as we talked about before, each node can send a message to itself. So the diagonal entries of this weight matrix have to be strictly positive. Okay. Secondly, because we are assuming that the graph is undirected, right? So Wij will be exactly equal to wji. Okay, so that means that in terms of the, again, linear algebra jargon, our matrix W is a symmetric matrix, such that W is equal to W transpose. Okay. And another point is that if the ij is an edge, that means that there is an edge between I and j, so they can communicate. Okay, so we associate that with a non-zero weight. Okay, so therefore, if there is an edge between two agents, they can communicate. So the weight is non-zero. Okay, so it means that wij is equal to wji, which is something that is not equal to 0. So therefore, if there is no edge between two agents, we can model that by saying that the weight associated with that edge is 0. Okay. All right. So we're also going to do some normalization, which is a standard. So we're going to assume that each agent j is going to normalize the weights for incoming messages, such that the weights of the incoming messages sum to 1. Okay, so it's basically, again, the importance score I'm imposing on the messages I'm receiving from others. Okay, so that means that sum of wij's over I is going to be equal to 1. So again, note that this notation means ij means that I'm sending from I to j. So if I'm normalizing the weights for incoming messages, the sum has to be over I. Okay. In terms of the matrix notation, this is the equivalent way of writing this normalization assumption. So that means that the vector of all 1 transpose times W is equal to the vector of all 1 transpose. Okay. And just sort of a fun fact, a matrix that satisfies this condition is called a column stochastic matrix. Okay. Now, because we are assuming that the graph is undirected, which means that W, our weight matrix, is symmetric, the implication is that if I'm imposing this normalization, which means columns sum to 1, okay, rows should also sum to 1 as well. So that means that the sum of wij over j now is also equal to 1. In terms of the matrix notation, that means W times 1 is equal to 1. And matrices that satisfy this condition are called row stochastic. Okay. So the first condition therefore means columns sum to 1. The second condition means rows sum to 1. All right. So our W is both column stochastic and row stochastic, therefore. Okay. And a matrix that is both row and column stochastic is called doubly stochastic. Okay. It's just some terminology. All right. So one question that could arise is that whether there exists graphs or weight matrices that are doubly stochastic, and the answer is yes. So here's an example. So if you have any connected graph, let's set the weights to be as follows. So set wij to be the reciprocal of the maximum degree of I and j. So this is how we would set wij when I is not equal to j. And because we are imposing this assumption that the rows sum to 1 or the columns sum to 1, as soon as we determine all of the non-diagonal entries using this formula, we can easily also determine the diagonal entries. So diagonal entries will be 1 minus this sum. Okay. And so what's the degree? So in this case, because we are assuming that the degree is basically the number of outgoing edges, right? So from a node. We are assuming that each agent can communicate with itself, which basically means that there exists an edge from one agent to itself. Also, we are assuming that the graph is connected. So any agent is also connected to at least another agent. So what does that mean? It means that the degree of each node is at least 2. Okay. So the largest Wij therefore can be is 1 over 2, using this way of setting the weight matrix. All right. So let's look at this simple example to see what's the weight matrix according to this formula. So I have 5 agents here. Okay. So let's try to determine the weights of each edge. Okay. So let's look at this edge. So in this edge, again, this will correspond to, so let's say I name these agents 1, 2, 3, 4, and 5. Okay. So W13 will be exactly equal to W31 because I'm going to assume that it's an undirected graph. So, and this is a non-diagonal entry that I have to determine. So using this formula, I go and check the degrees of node 1 and node 3. And I notice that the degrees are, so each node has 3 neighbors. Okay. So for instance, 1 is connected to 2 and 3, but also 1 is connected to itself. So the degree of node 1 is actually 3. Similarly, the degree of node 3 is also 3 because it is connected to node 1 and node 5, but it's also connected to itself. So therefore, for both, the degree is 3, and this value will be 1 over 3. Okay. So similarly, W12 equal to W21 is equal to, again, 1 over 3, because, again, both have a degree that is equal to 3. Okay. Now, let's look at W35, which is equal to W53. In this case, the degree of node 3, as we just talked about, is equal to 3. However, what's the degree of node 5? It is, how many neighbors does it have? It is connected to 2, 3, and 4. So 3 external neighbors, but it is also connected to itself. So the degree of node 5, therefore, is 4. So it means that, according to this formula, the weights will be 1 over 4. Okay. So similarly, this will be 1 over 4. And this will also be 1 over 4. Okay. So we calculated all of these non-zero, non-diagonal, off-diagonal entries. Okay. So for the diagonal entries, as we talked about, we use this formula. For instance, the diagonal entry, basically the weights that node 4 associates with itself, W4 will be just 1 minus 1 over 4. Okay. Or here, so W11 will be 1 minus 1 over 3 minus 1 over 3. So it will be 1 over 3. And similarly, we can calculate the other diagonal entries of this weight matrix. Okay. So therefore, we do have examples of graphs that are doubly stochastic. And as we're going to see, this assumption is going to basically help us simplifying the analysis. But nonetheless, it is an assumption that to some extent it is not very, very strong. And it helps us to basically model the performance of optimization algorithms for decentralized deep learning. So in the next video, we're going to talk about a simple algorithm for these scenarios. I'll see you next time.